Back on the Nintendo 64, artists needed to be really good at math. And it's because of an awesome design quirk of the Nintendo 64's hardware. Almost the entire process of rendering on the Nintendo 64 is handled via this one simple math formula, and mastering it will let you use crazy effects like appearing paths, much higher fidelity textures, or even more modern effects like bloom, and modern material properties like reflectiveness. I have always felt that the hardware designers for the Nintendo 64 don't get enough credit for how, possibly unintentionally, awesome its triangle coloring hardware process is. On a modern hardware, you get programmable pixel shaders. They are small programs that assign each rendered pixel an output color. The Nintendo 64 is from a time where fully programmable shaders were too expensive to run in real time. So instead of a shader, they had a fixed function pipeline. You can think of a fixed function pipeline as a shader with a pre-made math equation that you can only edit the parameters of. And this neat little combiner formula is at the heart of it. You get one subtraction, one multiplication, and one addition per cycle, and a maximum of 2 cycles that will run on each output pixel. For the rest of the video, I will visualize the combiner using the Fast64 Blender plugin, which lets you play around with them in Blender. You also only get one texture in one cycle mode, or 2 textures in 2 cycle mode. If you want to combine textures in any way, it has to be done via this math formula. For example, you could multiply a vertical gradient with a horizontal rainbow to get an output like this. And while this sounds very limiting at first, this simple setup is enough to generate some serious complexity. You can get very creative with this and pull off effects that at first seem impossible from such a simple formula. I want to show you some of my favorite creative render setups and some ways you can completely break the math formula for special effects. But before I can get there, we need to start simple so we're all on the same page. Let's vertex color a grayscale texture. So you get your texture input here and multiply it with your vertex color input here, and now you can vertex color. This is basically the standard combiner you would see on almost every asset in almost every N64 game because of how simple and versatile it is. It does let you color in grayscale textures, but the devs also love to use it on already colored textures to add hue transitions. In the Nintendo 64 scene, we call this puking a rainbow. Majora's Mask's underground section is a great example of it. One step in complexity up, but still very simple, let me show you how the Peach Bowser painting blends their 2 textures. The equation for the combiner can actually easily be modified to be an interpolation between 2 variables. Let's say you want 20% of one texture and 80% of another texture. The simplest way to represent the math here is with the generic interpolation formula. You can simply rearrange this math formula though and end up with exactly 1 subtraction, 1 multiplication and 1 addition. Perfect for our combiner. We can pass the percentage of each texture via any value we would like. The most convenient ones on the Nintendo 64 hardware are the 2 color inputs, primitive and environment, or even an LOD fraction that automatically moves between 0 and 1 depending on how big the texel pixels are in the final output image. Mario 64 used this LOD fraction value here, so they didn't even need any code to make the Peach Bowser painting animate. Building off the previous combiner, we can actually also use a per vertex alpha to blend our 2 textures. You can see this used a lot in Banjo-Kazooie. We can even draw 2 textures at different scales to have one texture give detail and the other one give shape, and then fade them out and in as desired. This gets you some rather complex surfaces already. And then, if we're feeling fancy, we can use the second cycle to apply a layer of vertex colors to get some crazy amount of visual variation out of a simple Nintendo 64 size texture. Some games get enough mileage out of just this one combiner to draw entire scenes. So far so good. These are all techniques you would commonly see in retail games. But everything from here on out will be niche tricks that I personally have not seen in retail games, and I believe that artists during the Nintendo 64's runtime largely did not use these, because for everything past this point, you will need a good grasp of how mathematics and art can collaborate to make an N64 material. Before I show you that, I have to shout out today's sponsor, Red Magic. Red Magic makes phones specifically built for gaming. They've sent me the Red Magic 11 Air, which has 16GB of RAM and a 144Hz 1.5K resolution OLED display. Lots of people keep asking me to play my game Return to Yoshi's Island on Android. This phone is easily strong enough to run my game through an emulator, but all the Android emulators are just too damn inaccurate to render the game correctly, and most fail to even boot the game. Even emulators on PC either need hacks or a high degree of accuracy, which means a lot of processing power that some people don't have available. This phone is strong enough to run a Windows translation layer that then emulates a super accurate emulator, Simple64, to a point where it can run my game at almost half frame rate. Not bad. This ROM makes it notoriously difficult to emulate because we use a custom microcode. Simple64 emulates the RSP and RDP directly, meaning it takes hundreds of times longer to draw triangles. This is easily the strongest phone I have ever held in my hands. Typically on the Nintendo 64, you would see 32x64 or sometimes even 64x64 textures. But the combiner can also be used to get much higher resolution textures looking good. Few people know this, but the Nintendo 64 can actually render 64x128 textures. Look at all these pixels. The only downside is you only get 16 evenly spaced steps of grayness on these. So our texture here would look like this, completely unusable. But the combiner can save us here. We can simply crank up the contrast on the base texture and then in the combiner multiply its brightness by a low number using primitive alpha for example, and add a base value to it using primitive color. 2, instead of 16 steps between white and black, get 16 steps between two different shades of gray. This lets us get much higher precision on a multitude of texture formats despite the Nintendo 64's pitiful 4KB texture memory. And of course you can combine this technique with most of the previous techniques if you want to use higher resolution textures there. Now, I have a secret to confess. There is more to the combiner than I have let on so far. And the attentive viewer will have thought about this one already. Some of you may be wondering, this formula can easily evaluate to something outside of the 0 to 1 range. For example, you could simply subtract the color from 0 to get negative value. What happens then? Well, for a while, nothing. All values between minus 0.5 to 0 get mapped to 0, and all values between 1 and 1.5 get mapped to 1. This is because there's a hidden 9-bit math happening under the hood. But once you go beyond these thresholds, the values wrap around. Some might consider it a bug, but it is secretly extremely useful, and the modern Nintendo 64 scene has been using this to great effect. Look at this glistening water for example. Light spots appear and disappear quickly. Well, we can take two noisy textures, multiply their alpha, and subtract the result from 0 in cycle 2. This will underflow only when two bright pixels in the noise textures overlap. Then we can scroll the two textures in different directions, and we get these bright spots to appear all over the place nearly randomly, which looks just like real glistening water to me. If we wanted to, we could then additionally multiply this with the primitive LOD fraction or a vertex alpha value, similar to the Peach Bowser painting, to get Mario's Sunshine-esque water. Here's a video Rovat made about this technique. Similarly, we can use the combiner's clamping without overflow on purpose. What if, for example, I wanted a big sail that's only ripped at the bottom? A naive approach would be to have two different textures, one opaque and one with an alpha channel rendered in cutout mode. When we render in cutout mode, any pixel with an alpha value over 0.5 is rendered opaque and the rest is discarded. But there is a fancier way. We can multiply the texture's alpha by 0.75 and add vertex alpha to it. We can then vertex paint the alpha to 75% opacity at the top and 0% opacity at the bottom. This maps the range of the top part to values between 0.75 and 1.5, which is all opaque, and the bottom will evaluate to values between 0 and 0.75, which still allows opacity, but cuts out any transparent pixels. This same principle can also be applied for dynamically shifting vertex alpha values. Take a look at this cool thing. I used the same clamp trick and an additive hexagonal pattern like this, and then set the vertex alpha depending on the vertice's distance to Mario. This lets us get the alpha fade-in effect per vertex, and it is an extremely cool and actually kind of cheap effect I like to use in multiple places in my game. Another way to use clamping is to peak your colors out. For example, by just adding a dark primitive color. After you hit full brightness on one color channel or one bright pixel of your texture, other pixels and color channels keep increasing in brightness, which effectively looks as though the sun is hitting these particular spots extra hard. L'Oreal is the master of this technique, and you'll see it is used to great effect in their mods. Similarly, I use both overflow and underflow clamping to the absolute max with my coin combiner here. Any increase to my color input and the color underflows or overflows, or we lose saturation. It makes these coins look super shiny, even though they are just one single grayscale texture. Getting into even more complicated territory, look at this bloom implementation on the Nintendo 64. I bet you've never seen anything like this. It looks like Twilight Princess. The way it works is, as by now you should expect, via the combiner. Because well, there's nothing saying that the video output buffer itself can't be a texture too. This is a two-step process. First, Tharo takes the entire rendered output buffer and renders it again at half resolution. We go through this process 3 times to get from a 320 by 240 screen down to a 40 by 30 texture. Then, on the second step, we load our originally rendered frame in small chunks as one texture and our downscaled 40 by 30 frame buffer as a second texture, and run the combiner on this to add the blurred image to the original frame buffer. Tharo chooses to have one cycle that lerps between the blurred texture and the original frame buffer, and then a second cycle that adds some percentage of the blurred picture to the original picture. The result is that any bright pixels will be blended into the surrounding environment, and all bright colors peek out similar to the previous combiner, which is exactly what you would want out of a bloom effect. Another modern effect you can get is a reflectiveness texture. See, there's a texture format on the Nintendo 64 known as Intensity Alpha. This format reads one image split into an intensity channel and an alpha channel. These two channels can effectively be 2 entirely different images. Doing this for both texture 0 and texture 1 effectively lets you use 4 textures at the same time. There's some really cool results we can get from that. For example, let's say we want to have a building with a reflective surface. We can store the building's base color into the first intensity channel and the amount of reflectiveness each pixel takes in the alpha channel, and the reflecting texture, in my example, is Starry Sky, into texture 1. Then we simply multiply the texture 0 alpha channel with the reflecting texture 1, and afterwards I like to scale it down a little bit with the environment color factor, similar to how we increased the fidelity of the texture much earlier in the video, and add this to the base color of the building. This gives us some really nice looking reflections. Akumoid helped me refine and draw this material here, so shout out to them. On top of that, we still have our fake 4th texture slot open. Unfortunately, I have not found a use case for this one yet, but I'm sure it exists. One idea would be maybe to combine the previous ideas with this emissive material Biobag made, which by the way also works via adding the texture's alpha channel multiplied by the light color to the material's output. One issue though, at this point our combiner is almost fully utilized, so that it becomes difficult to find space for something like vertex colors. But it is not entirely hopeless, because we can use negative colors. We can put the vertex color into a subtractive slot here, and then transform our vertex colors into negative space. Red becomes turquoise, to use vertex colors after all. Of course, that does mean that we are more limited in our light or vertex color range, but the effect is worth it. This actually comes in clutch often to save rendering the second cycle as well, as the 2-cycle mode is slower in most conditions. And these are just some ways you can use the combiner. There are literally billions of setups, so I'm sure we will continue to see innovation. I haven't even touched on some of the crazier combiners yet. Maybe I will do a top 10 favorite combiners video at some point. You can even play around with it yourself if you download the Fast64 Blender add-on. If you try it and make something cool, be sure to show it to me on Twitter or Blue Sky. I will also say that this is all just one aspect of the Nintendo 64's render pipeline. There are also blend modes, a lot of RDP render flags, and custom microcode. Not to mention all the infinite possibilities CPU render support can bring. Ever seen normal maps in an N64 game? Or even a full PBR setup? With CPU rendering, it is super easy to pull off without any deep knowledge at all, although that latter one is kind of expensive. Thanks for watching. If you'd like to see me use these, follow development here on YouTube or on my second channel where I stream weekly. Shoutouts to all patrons for supporting this channel, and to Red Magic for sponsoring this video. The game I've been showing in the background is Return to Yoshi's Island, running on the Red Magic 11 Air via a cycle-accurate emulator, running inside a Windows emulator. emulatorception. And I'm currently working on the overworld. All main courses are done, but lots of work is still to be done. I want to remove all Nintendo code for one, and then there's also lots of beta testing and Bioback's polishing touches. Until then, bye bye.